Welcome back to chapter 18. We are spending our time now in section 18.7, which is a rather complex section with very important information. First, I'd like to draw some parallels to actually chapter 16. Remember, chapter 16 talked about pericyclic reactions, including Diels-Alder reactions. And at that time, we were already introduced to electron withdrawing groups and electron donating groups. Okay, I'm going to switch over to my ChemDraw program here. So I've pre-drawn some molecules. When we are looking at these structures, and we had actually these four were good dienophiles, but I added another one because for us it becomes really important to understand to the fullest extent what the electronic nature is of a group. So whether this is a ketone that's in conjugation with a double bond, and now instead of looking at the double bond, basically what we're doing is, and I could just quickly do this, these molecules, these four molecules were great dienophiles for Diels-Alder reactions, but now we're trying to understand the parallels as to what happens when these groups are present in an aromatic ring. So let me just copy this over. So the molecules that we are considering, and now I'm making these aromatic. Let me try this again. That did not work so well. I need to make a little bit more room here. Okay. So instead of now having just a double bond, we're talking about aromatic structures, right? So we now want to understand the electronic effect of having certain groups present. And let me snag the right bond here, to which I can fuse on the benzene ring. Do this 2 more times. And now, of course, the names are no longer adequate. And so now we're dealing with benzoic acid, benzonitrile, and anisole. And here we have the R as a placeholder. So this could be an aldehyde or a ketone. This could be a number of different esters. Here's benzoic acid, here's benzonitrile, here's anisole. And I've also come up with a drawing that kind of summarizes some of the properties. But our structural drawing ability is going to play an important role. If we're only looking at these semi-condensed structures or just the general placeholders, we have to have an understanding as to what's going on, especially in the alpha position. So here's the benzene ring, what's attached. This carbon is involved in a multiple bond, in a double bond. That actually makes this electron withdrawing. Here, the same thing, just a different substitution on the side. Here, the same thing. And here, I cannot see this, but when I see this abbreviation, immediately I should think about the fact that the CN bond is actually, and let me just draw out a more detailed drawing. Now I'm going to introduce a triple bond to nitrogen. I need to see, okay, this carbon here in the position 1 that is attached to the benzene ring, there's now a multiple bond there. I also have an electron pair, but that's one more atom further, so I can show the electron pair, and I'm encouraging you to do this. But because of this multiple bond, we also know that this electron density can be changed, and whenever we have a multiple bond, it actually means that there's an electron withdrawing effect, because there's a way of taking away electron density from the aromatic ring. So you can draw a resonance form that has a positive charge on carbon and a negative charge on nitrogen. You can do the same thing for all the carbonyl groups in these other compounds. And then the last one here, we now need to, most importantly, need to recognize that we have basically 2 free electron pairs, and that's electron density that can be put into the aromatic ring. So thus this one, anisole, has this methoxy substituent that can put electron density into the ring and activate it. So these here, we're talking about deactivation, and this group here, the methoxy group, is just one example of having an activating electron donating effect in there. And I'm going to copy over these structures and paste them into our slide as we continue in the presentation here. Okay, so I've outlined that there are actually two effects that we have to be really careful about as we're looking at the aromatic ring. We can have an activating group, a deactivating group, and then the halogens, I refer to them as the Jekyll and Hyde kind of. They're not so easily classified. They have a little bit of characteristics of two important aspects. So the reaction rate, the speed of the reaction, how fast or how slow the reaction is. As we're looking at these groups, does the group speed up, meaning activate, or slow down or deactivate the reaction? And then the other part is regioselectivity. Regioselectivity has to do with the location, the direction of where the new group is attached. Remember, this is all about, we have not just benzene here, we have a mono or di or tri-substituted benzene, and where would the new group come in with the conditions we learned about. Both of these factors are influenced by electronic properties of the group present on the ring. As I said, electron donating groups, I abbreviate as EDG, or electron withdrawing groups responsible for the directing effect. I have likened this to a movie set where we have the director who tells all the actors where they have to be and what role they play. It's kind of similar that way. A group that is already present is going to have an influence as to where the new group is going to end up. And one important skill in here is that you need to be able to draw all electrons, meaning bonding and non-bonding electrons, in order to create a good Lewis structure. That's what I mean by Lewis structure. All electrons, bonding and non-bonding, to understand the directing effect. And that's why structural drawing abilities are really playing a paramount role in here. So make sure that you pay attention to this. Now, moving on, here we have a summary of directing effects. We have either a group that is an activator or a group that is a deactivator. I'm going to switch over to my ChemDraw program. So as I look at these structures in the upper right here, let me move them over a little bit. So I'd like to then talk about activators we can correlate to, let me try this again, to our substituents that will have an electron donating group, or they will have an electron withdrawing group. So I need to change that one letter. Okay. Here, please note that these arrows indicate where the activation is. In other words, these are not mechanistic arrows. I wish they had used different kind of arrows for this depiction, such as, let me just pull one up. This one would have been better, in my opinion, to show where a position is activated. So we have the ortho and parallel positions for those groups that are activating, and then we have the meta position for the groups that have an electron withdrawing nature. And what this is showing, basically, in each of these positions where the arrows are, that there's a delta negative charge. Okay, and let me see, I'm not sure whether I have a delta negative easily handy, so I do not, but I'll leave it out. So these are partial negative charges, which means that addition in these positions is going to be more likely. And I'm going to cut and paste this into the main slide. All right, moving on. So I have here a table, and you have equivalent information in the textbook, and in different ways it's represented. You may want to pause here and take in the many structures that are in here, and then I would also encourage you to particularly pay attention to everything that's in this row here and carefully read through it, and then make that correlation to the structures that are shown in each column. As you can see, we're moving from strongly activating to moderately activating to weakly activating to weakly deactivating to moderately deactivating, strongly deactivating, and maybe I'm going to use a different color. And then here we have ortho-para directing and meta directing. Okay, I've also highlighted, and while we're at it, let's add more color to our life. So we see that there can be activating and deactivating effects and how these cross over. You see how the halogens are kind of the Jekyll and Hyde situation. I've used a placeholder here. Basically, through an inductive effect, halogens will deactivate, but once the reaction happens, halogens have an electron pair that can help stabilize any kind of charges in the reactive intermediate. That is the key part of halogens. So they will be deactivating at first, but they are going to be also para-directing as to how they can use that electron pair to stabilize the intermediate. So I would pause here and take in the structures and carefully pay attention. You can also see that whenever we have a multiple bond, we have the ability to take electron density away. As I just mentioned, nitrile is one of those. Here, sulfur, there's a multiple bond. There are actually two. And here we have all the carbonyl groups. Okay. Also, your success will depend on understanding this kind of unusual structure, the nitro group. Nitrogen can only have a maximum of 4 bonds. And how to basically be able to draw that structure. And when I see that there's a positive charge on the first atom, I can now also draw the parallels to an ammonium substituent, which is what this is. There could also be R substituents here. And if we have halogens, that's going to place a partial positive charge on this first carbon. So all of these are strongly deactivating. Okay, so try to make sense of these aspects as you navigate this. And again, the best way to do this is through lots of practice. On the next slide, we now are going to go through in very great detail. And you may want to stop here, first look at the structures, but I'm going to walk you through all the aspects now. So in this segment, 18.7, we're going to talk about the activating groups first. Here we have 2 issues that arise when we're adding a group to the ring. This one will have an effect. So what is the effect of the methyl group on the rate of the nitration? We know that toluene actually reacts much faster than benzene. And that was kind of the conundrum, the challenge with Friedel-Crafts alkylation reactions, that once you have a group on there and you're trying to introduce more, you can get polyalkylation. Now here in this case, we would be adding a net NO2. We would replace one of the hydrogens with an NO2 group, a nitro group. So the CH3 group is electron donating, therefore it makes it a better nucleophile. Remember how we're using one of these double bonds to now form a new bond to our placeholder electrophile. Next slide. As we're looking at this, we want to also understand the effect of the methyl group on the regioselectivity, which is the placement of the new group. Is it going to be in the ortho position? And we have 2. In the meta position, we have 2 positions, and or the para positions. So there are 3 possible products, and here we are. It could be ortho, meta, or para. But we now are looking at the electronics to be able to predict which way this is going to go and which products are more likely to form. So it turns out that with activating groups, we will have ortho and para being favored. Actually, para is mostly favored because in some reactions because of sterics. When we're looking at this here, we have very little meta product formed. You see that this is only 3%. The major product is actually this one here, the ortho. Okay, and then the next highest up, so this kind of a 2-to-1 ratio, would be the para. So this is a typical ortho-para situation. Now, how can we rationalize this? And here is again where mechanisms are our friend. We can look at the electronics as to a thought experiment. What would happen? So if we're now adding in the ortho position and the para position, as we're looking at these ortho, meta, and para, we not only want to look at the number of resonance structures that can form, that can definitely play an important role, but we also want to look at the overall stability of the sigma complex intermediates. So the relative stability of the sigma complex intermediates. So you do your error pushing mechanisms. I would stop here or pause the video, look at the starting material and the alignment, and then just form the product and then kind of reproduce the resonance forms that are possible. Looking now closely at the structures, we find that we have different quality of intermediates. So if the nitro group was added in the meta group, we would have these three sigma complexes. Look how the sigma complexes places the charge. I'm going to use a different color here. So here we have the positive charge on a secondary allylic carbon, secondary allylic carbon, secondary allylic carbon. So now we're using a concept that was often used in Orgo 1, cationic or carbocation stability. Let's compare that with the other structures that are available, notably from ortho and para attack. Let me switch the color again. So here we have allylic secondary and allylic secondary. Okay, so we had two here. However, the third structure is tertiary allylic. Okay, when we look at the para attack, we have secondary allylic, and tertiary allylic. So these are much higher quality, much more stable intermediates, and that's why we can now say, okay, ortho and para attack are favored. We can also express the energetics in a diagram. You have your energy on this axis where we now are placing these, and because of the quality of the intermediates that are being formed, we can now make an assessment. Here we are. Tertiary and tertiary are low in energy compared to only secondary allylic. And that's why the meta attack is not favored. All right, the sigma complex obtained from ortho-para attack has positive charge delocalized adjacent to the electron donating methyl group. Electron donating effect is an inductive effect here, which means that the electron density is only experienced through a single bond, not through a double bond. That's an important distinction. Induction, the inductive effect, is weaker than a resonance effect. Nonetheless, the methyl group will have a profound influence in favoring the ortho and para attack. You may want to pause here to just think this over and then move on with the presentation. So, as we're looking at this, these were the results. More ortho is formed because there are two ortho positions and there's only one para position. Remember how there's symmetry in here? So that will also affect the overall outcome for this. On this slide, we're now looking at a methoxy group. Remember how I'd shown you a couple of slides ago, and that it was really important that we fill in these electrons here, because now we have a benzene ring. The next group has an electron pair available, and that is what makes this electron an electron dodenate group, and therefore an activating group. So the methoxy group in anisole, that's the structure here, activates the ring 400 times more than benzene. The methoxy group donates electron density via resonance. So that's a much stronger effect compared to an alkyl group where we only have an inductive effect. On the next slide, as we're walking through this, so what would happen if we were to use a methoxy group that activates the ring? We don't even need a catalyst. See how this now just reacts with bromine? We don't even have to add aluminum bromide or iron bromide. And polysubstitution is also something that can happen. As you can see, we get a quantitative yield, 100%, of replacing both the ortho hydrogens and the one para hydrogen with a bromine. So like the methyl group, the methoxy group, OCH3, is activating and ortho-para directing. And here are some of the yields that we would encounter if we were to use a different set of conditions. Remember how these conditions here will be a nitration where the electrophile is NO2, plus. Not very pretty, but you can also hear me as I'm presenting this. So we see that there's a 31% ortho directing, and then we have 67% para directing. Here, para is the major due to the ortho position being more sterically hindered. Remember that when we're looking at anisole, and maybe I'm going to quickly switch over to my ChemDraw program, as we're looking at the methoxy group. So here's anisole. I can redraw that methoxy group, and let me just quickly do this. So this would be O. I'm making a new bond to a carbon. Actually, I want to make this a little bit longer. And then here we have our CH3 group, so CH3. But what I'm changing here is I'm going to draw out each hydrogen. Let me change this again. I want to have the same length for this one. So we have to understand that there is a steric component with the methyl group. So this can rotate, but this is going to take up more space. And that's why when we go back to maybe this bond, I'm going to adjust it a little bit better. All right. But there's some real sterics that we have to consider in this situation. So I'm going to paste this in here. So let's place this here, right? So we have a semi-condensed formula, but there are sterics here. And if this was a T-butyl group, the effect would be even greater. But that's why we see a higher percentage of now the para product. Okay, as we can do the same analysis again, you may want to pause here, maybe look at the initial structure and try to now show the result of this curved arrow, of these two curved arrows, and then draw the resonance forms. And here what we see again is not only the number of resonance forms, but the quality of the resonance forms. And when we look at the ortho and para attack, we find that we can actually, we have the positive charge here next to the oxygen. We can distribute it around the ring, but we also can place the positive charge on the oxygen. And because of now this additional resonance effect, that's why we have a fourth sigma complex available, and that makes the ortho and para attacks more favorable. So this is just another example where your ability to deduce the answer based on the electronics and the stability concepts you're familiar with, to apply them here. And so speaking of stability, we can look at the number of and quality of resonance forms. And then as we look here, we again can assess the energy levels, and we see this is reflected in having this charge in the positions they are in after ortho addition and after para addition. This puts this much lower in energy compared to the meta attack, where the electron pairs that are in here cannot be pushed into this bond. That's what this is mostly about. Okay. So let's practice. Predict the major product for the following reaction. You may want to pause here, copy the structures, remember the conditions, and then not only identify E+, but then also draw the product. Let me switch over to ChemDraw, but you can pause and take your time to work through this as you practice the skills that are necessary to come up with a good answer for this. All right, I think I had this. All right, so here are the two questions. So here we have our benzene ring. We know that this delivers, basically, this is a way for introducing Cl+. And I'm going to draw it like this. So now, this is an ethyl group, this is an R group. We know that this has a moderate electron donating and activating effect through induction. That was the weaker effect. Okay. So this now indicates that the positions that are favored would be ortho or para, right? So those are your main products. It's an ortho-para director, and then you can draw that out in your solution. When we're looking at the second example, here, what is important to recognize, and I would like to now redraw the structure here. Actually, I should say that in one of the handouts that I provided for the lecture portion, this question was actually simpler because I had provided, this was basically a multiple choice question. So you could then review the structures. You should be able to do both. So this is really it. So this is our chlorine Ned addition. And we had learned that for moderately activating R substituent, a rest group, an alkyl group, that the correct answer in here would be number 1. Para is preferred. Okay. So let's go to this example. This looks a little bit more complex, but we can apply all the other things we've already discussed. I'm going to take a minute here. I'm just going to redraw the structure. We have this kind of substitution, and then we need to fuse on another ring in this ChemDraw program. All right, that looks almost like it. Now we have this NH, so I can just hover here. It will put in the NH, and then I need to fit in a multiple bond, a double bond for 2 oxygen. So here we are. Okay. I sometimes like to draw out that NH bond, makes it a little bit clearer to analyze. And remember what I said about Lewis structures? We want to show bonding and non-bonding electrons, so that means I have to show electrons here, show electrons here, and show electrons here. I also indicated that as we're looking at this, and I want to, let me paste this over because then I can better highlight. So I'm going to copy the structure over to the PowerPoint presentation. All right, here we are. Let me increase this in size. So, as we're looking at this, I didn't want that highlight to be there. Let me see, can I do this differently? I need to find my eraser and get rid of this. I don't want to confuse you. And as we're looking now at pasting over the structure, here it is. Again, anytime you can pause the video. Now, what do we pay attention to? We have 2 aromatic rings. We have this one, and maybe I should pick another color for the other one. And then we have this aromatic ring. Okay. So what's going to matter now is what is here in this aromatic ring the next position over. So we need to look at this one here and ask ourselves, what is the effect of that group? And then we look at this position here and we ask ourselves, what is the effect of that group? I see here the carbon directly connected to benzene is connected to an oxygen in a multiple bond. Ding, 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 ding. That's an electron withdrawing group, which means that this orange ring is deactivated, and that your substitution is going to be preferred on the activated ring, which is the green ring. Again, as we're looking at the position, 1 bond over, we see a nitrogen and we see electrons here. I see electrons here too, but they're not in that position. They're further away, right? But these electrons can be pushed into this ring. So when we look at our scheme, this is an electron donating substituent. It is also para-directing, and then we have to find this. We can also look at the green ring and the orange ring and say, well, there's an additional substituent, which is, this here, but it kind of cancels each other out. It's these 2 are the key ones to then assess, and that's how you can figure out where the net Br plus addition is going to be. So to sum up this complex segment, Here's again a summary of all the directing effects. Please take time. It will be time well spent to understand these electronic effects, from strongly activating all the way to strongly deactivating, understand the special role, my Jekyll and Hyde group of halogens in here, and kind of analyze the material I've written down in the segment down here. And just to go back, your structure writing ability is going to play a very important role. If you don't understand that an NO2 group has this kind of breakdown, you will always get tripped up by not understanding the electronics, especially in this very reaction and mechanism heavy chapter. And then let me just switch over. So as we're looking at the NO2 group, and I've drawn a kind of a nitromethane. But as we're looking at the structure here, what I want to drive home is that if this is just an R group, and this is what this is about, or better yet, an AR, an aromatic, this is not nitroargon, this is the automatic system. This is an abbreviation placeholder for the aromatic group, but you have to understand that there are electron pairs associated in here. Let me grab this tool correctly. So we have 2 electron pairs here, we have 3 electron pairs here, and that the charge on nitrogen, it's going to stay that way. We cannot have a double bond in the structure. If I was to draw a double bond, and I mentioned this before, I'll just copy this over and draw an incorrect structure for you to see how this could not be a feasible arrangement. If I'm drawing a double bond here, and you might think, well, but it eliminates the charge, we would now violate the octet rule in this position, because nitrogen is incapable of holding this many electrons. That's why one of the double bonds needs to break open, and we have these 2 charges. Okay, and we'll leave it at that for this segment.